All right, so we're in 15.7. Oh. Talk about the divergence theorem as soon as the screen comes on. It's always exciting when we get to this point because what we'll do tomorrow is talk about how Green's theorem. We talked about the fundamental theorem of line integrals, Green's theorem, the divergence theorem, and then Stokes' theorem. How they're all kind of one version or another of the fundamental theorem of calculus. So we've kind of come full circle from Calc 1 with the fundamental theorem of calculus and evaluating integrals to these other forms of the fundamental theorem of calculus. All right, so let's do a quick recap of surface integrals. So we started talking about scalar surface integrals. So the integral over S f of xy ds. Our procedure here was we parameterized our curve, ds, we parameterized our curve. We express f in terms of our parameterized curve. And we said that became the integral over a region in the xy plane of f of xy, and ds was if our surface was z equals f of xy, ds was the square root of g sub x squared plus g sub y squared plus 1 dA, where z is some f of xy. So we have our surface parametric representation of our surface, and this is our scalar surface integral. And then we said yesterday for a vector surface integral, so this is a scalar surface integral. For a vector surface integral, we're talking about a flux integral. And we said that our flux surface integral was the integral of f dot n ds. So we're summing the normal component of f times our little area element over our surface. And for this integral, we wanted, if we have z equals f of xy, we said that capital G of xyz was z minus f of xy. And this flux integral was the integral over our region in the xy plane of f dot del g dA, where r is our region in the xy plane. And this is how we're going to evaluate a flux integral if we have z equals f of xy. And we came up with expressions if we had a parametric surface. We had r of u and v. Similar expressions. Most times we're going to be talking about surface integrals in this form. So there's a quick recap of how we found our surface integrals. And we said a couple of important things about the flux integral. Is when we evaluate this is a double integral. So our integral needs to be expressed in terms of, if we do it in this form, in terms of x and y. So anytime we see a z, we're going to substitute for our z to get our double integral in terms of x and y. All right. So we good with our little recap of our surface integrals. And we interpreted this one. We said we can interpret this one several different ways. If our function f of xy is a mass per unit area, then the surface integral would give us the mass of our surface bounded by this region in the xy plane. Or if it was a charge per unit area, this would give us the total charge on our surface. And we set our flux integral. This represented the flux, and our flux is the volume per unit time flowing out of this surface. The flux, we interpreted flux as the volume of a liquid, some kind of fluid, the volume per unit time flowing out of the surface. And we said that this was the flux through the surface, the flux upward through the surface is another way you'd be asked this question, or just this flux integral. All right. So a little while back, when we were talking about Green's theorem, just to set up the divergence theorem, when we were talking about Green's theorem, we said that for Green's theorem, and just a reminder what Green's theorem says, it says the line integral around a closed curve C of m dx plus n dy was a double integral over the region bounded by the curve of dn dx minus dm dy dA. So we have this line integral around the boundary, and we related that to a double integral over the region bounded by our curve C. And we went through a process after we talked about Green's theorem we found the line integral of the normal component, the outward component of f around this closed curve. So we came up with this expression. So Green's theorem for our line integral of the outward normal component of f. We said that the line integral around this closed curve of f dot n ds was the double integral over our region of the divergence of f over that region. So we can think of this line integral of that outward normal component as the flux of f out of this curve. And our outward normal component we're talking about in the plane. And we related that to this double integral of the divergence over the region. We're going to extend this idea, the sum of the outward normal component. The sum of the outward normal component of f over a surface is our flux integral. So we're going to relate this line integral in the plane to our flux integral in space. And we're going to extend our expression for Green's theorem of this outward normal component of f to 3 dimensions to talk about the flux integral, and we're going to relate that to a triple integral of the divergence. So divergence theorem is telling us essentially what we figured out for Green's theorem in the plane. So I want to do this just to motivate the divergence theorem a little bit. All right, so the divergence theorem. The divergence theorem tells us that our flux integral, the double integral over our surface of the normal component of f times our little element of area, ds, equals the triple integral over d of the divergence of f dv. And for the divergence theorem, we're saying d is a solid region bounded by a closed surface S. And n is the outward unit normal vector. And sometimes you will see this double integral, this flux integral, over a closed surface S, written as double integral over S with a circle. The circle means it's a closed surface. A couple of important things about the divergence theorem. The divergence theorem is finding the outward flux over a closed surface. So our surface has to be closed. So the example we did yesterday, we found the flux upward through a surface. So the divergence theorem wouldn't apply to that situation. Just like Green's theorem has to apply to a closed curve. It's a mistake quite a few of us made on the last quiz. We tried to apply Green's theorem when we were talking about a line integral from one point to another. Green's theorem only applies to a closed curve. The divergence theorem only applies to a closed surface. So the examples that we talked about, you were asking about the cube in the homework. The divergence theorem would apply to that cube because the cube is a closed surface. So rather than having to evaluate that surface integral for 6 different surfaces, the faces of the cube, we can evaluate the triple integral of the divergence of f over the volume of the cube. And the triple integral over a cube is pretty nice because our constants are our limits of integration are just constant. So divergence theorem only applies to a closed surface, and n is our outward unit normal vector. So if our surface is a really complicated surface, this surface integral, the flux integral, can be really difficult to evaluate because we have to find our outward unit normal vector for the different parts of the surface. We have to add all those together. Instead, we can apply the divergence theorem and do this triple integral of the divergence. So what this is saying in words, what this is telling us is if we sum the normal component of f over our surface, we sum the flux, the outward flow of f over our surface, that's equal to the integral of the divergence over the volume of the region, over the solid of the region, over the volume of the solid. So the divergence is the divergence of our field in the solid is telling us something about the flux of the field through the surface of that solid. So the divergence is related to the flux through the surface. The divergence on the interior is related to the flux through the surface. And that's what we said back here. In the plane, the divergence through the region is related to the flux out of the boundary of the region. So the divergence is telling us about the flux, something about the flux of our field, the outward flow. Divergence theorem, you'll also hear divergence theorem called Gauss's theorem. Gauss proved this theorem first. but he didn't publish it until later. And you'll also hear it called Ostagrodsky's theorem. A Russian mathematician by the name of Ostagrodsky discovered it first. He first published it. And interestingly, he was denied a mathematics degree in Russia at the time because he was an atheist. So he never had a mathematics degree in Russia, but he was the first to publish the divergence theorem. And all this came about as electromagnetism was being developed. They were trying to develop a mathematical theory for electromagnetism. And you'll see the divergence theorem when you start talking about Maxwell's equations. The integral form of Maxwell's equations have these various kinds of theorems in there. Proof of the divergence theorem, not complicated, but it's kind of long, and it involves taking into account lots of different cases. So we're not going to do the proof. It's very similar to what we did in the plane with Green's theorem. All right, so let's look at a couple of examples using the divergence theorem, and then this is going to lead us to finally being able to come up with a physical interpretation of what the divergence is. We talked about the divergence in one of the first lessons in the chapter. We never really had an idea of what divergence is. All right, questions before we go on? Okay. So an example. We want to evaluate this flux integral of f over s of f dot n ds. And I'm going to rewrite this in another way that you might be asked this question. The outward flux of f through s, and we want to use the divergence theorem. So another way we would be asked this question, this flux integral, is to evaluate the outward flux of f through s, where f, in this case, is xy I hat plus yz j hat minus yz k hat. And s is the solid bounded by z equals the square root of a squared minus x squared minus y squared, and z equals 0. So first off, what is this surface? Sphere, but it's bounded below by z equals 0. So hemisphere. So what's that? It was bounded above by z equals 0. Well, this sphere would be, our center is at 0, 0, 0. So it couldn't be bounded, and it's radius a. So you're talking. So you said, what if we're talking about the lower hemisphere? Yeah. Could be the lower hemisphere. So let's see. Do we need to make our restrictions a little more precise? So we'd have to say 0 less than or equal to z less than or equal to a. Would that do it? So that's true. We could be talking about the lower hemisphere rather than the upper hemisphere. So we're bounded below by z equals 0 and above by, so we're going from z equals 0 to a. So this is an upper hemisphere. And the fact that we're bounding it below by z equals 0 makes it a closed solid region. So we're going to use the divergence theorem. So I'll just rewrite it here f dot n, our flux integral. ds is our triple integral over our solid region of the divergence of f. dv. So let's find our divergence. Divergence of f. Do you remember how to find the divergence? Divergence of f is del dot f. So we're going to do, just to rewrite it, d dx I hat plus d dy j hat plus d dz k hat. And we're going to take that dot product with xy I hat plus yz j hat plus or minus yz k hat. And we're taking the dot product, so our result is always going to be a scalar. Our dot product's never a vector. So our divergence of f is d dx I hat. So we just get y plus d dy of j hat. So we get z plus d dz of k hat. So we get minus y. And we end up with z. So this is looking better already, right? Our solid region bounded by S is our sphere, x squared plus y squared plus z squared equals a squared, and we're bounded below by z equals 0. So what does this tell us we're going to do for our triple integral? Spherical coordinates. So this is going to be really nice. We're talking about a sphere, spherical coordinates, and we're integrating z in spherical coordinates. Z equals sounds good. So we're going to use spherical coordinates. Z equals rho cosine phi. So we have our flux integral, S of f dot n ds is this nice easy spherical triple integral. 0 to 2 pi, 0 to, what's phi going to vary from? 0 to pi halves. And our radius, rho, varies from 0 to 8. Rho cosine phi, rho squared, sine phi, d rho d phi d theta. And this whole thing is my dv, rho squared sine phi d rho d phi d theta. So I end up evaluating my rho integral is just rho to the third. So I get rho to the fourth over 4, evaluated from 0 to a. So I end up with a to the fourth over 4 from my rho integral. And we're going to evaluate our other integral, 0 to pi over 2. And I have a cosine phi, sine phi, d phi d theta. Nice, easy phi integral. I'm going to say u is sine phi, du is cosine phi. So we have a sine squared phi over 2. So this turns into a really nice integral. 0 to 2 pi, and we're evaluating sine squared phi over 2 from 0 to pi over 2. Question? Oh, I was jumping ahead to that one. A to the fourth. And then this is d theta. And sine squared pi over 2, we end up with a At our upper limit, sine of pi over 2 is 1. So we just end up with a 1/2. Sine squared of 0 is 0. So we end up with a factor of 1/2 there. A to the 4th over 8. Integral from 0 to 2 pi d theta. This just adds a multiple of 2 pi. So we end up with pi a to the 4th over 4. So our flux through that solid surface would be pi a to the 4th over 4 units of volume per unit time. If we're thinking about this as a fluid flowing outward from this sphere. So if this field represented a velocity field of a fluid, this would tell us the volume of that fluid per unit time that's flowing outward from that surface. And I think evaluating that triple integral, not difficult. To find the flux using the surface integrals, we'd have to find the flux through the hemisphere, and we'd have to add the flux through the bottom portion of the hemisphere. So we'd have to do two flux integrals to find the flux through our solid surface. All right, questions there? So when we have a closed surface, it is often much easier to evaluate this triple integral than it is to evaluate the surface integral. Sometimes the surface integrals can be difficult to evaluate. So this can save us a lot of work. All right, questions there? All right, the last thing I want to talk about with the divergence theorem is finally a physical interpretation of the divergence. All right. So let me just to rewrite, I want to start with the divergence theorem. The divergence theorem is going to give us a way to come up with a physical interpretation of the flux of a field, vector field. So the divergence theorem says the flux through the surface is the divergence equals the sum of the divergence over the volume. So we're going to think of a tiny surface, very tiny surface. Our flux, if we think of a tiny surface, our flux through this tiny surface, we're thinking of this, our flux is approximately, by the divergence theorem, our flux through that tiny surface is approximately given by del dot F delta V. So we're just talking about a tiny surface, and we're thinking about what the divergence theorem tells us. The flux is approximately equal to the divergence times the little tiny piece of volume, where delta V is the volume bounded by this tiny surface. So we're going to say that our flux, I'm going to write just in words our flux. So what we're saying is our flux equals the divergence of F times delta V. And I'm going to write our divergence. So our divergence of F equals the flux divided by delta V. If we let delta V become very, very, very small, so we take the limit as delta V becomes very, very small, in the limit we can say that and this is the flux per unit volume, so the flux per unit volume, we let delta V become very small. In the limit we say that our divergence is the flux per unit volume at a point. So our divergence tells us at a point the field's tendency to flow outward from that point. The flux tells us the divergence tells us the flux per unit volume at that point. And the flux is the volume per unit time that flows out of it. Yes?
Isn't there a Greek word for flux?
We don't use a Greek, in calculus we don't use a Greek letter. We'll leave that to the physicists.
But there is one.
I think there is a symbol. What's that? An I? I thought that's flux? Yeah? Because the I is also a moment of inertia, isn't it? That's also current, right? So this depends on the context. It gets like, it's like English, you have to interpret it by the context. Yeah, that's I do remember this, something like that. All right, so our divergence, so this is our physical interpretation of the divergence. It tells us the flux per unit volume at a point. So the tendency of our field will cause an outward flow at a particular point, and the divergence tells us the quantity of that outward flow at a particular point. And we can classify our field by the sign of the divergence. So if we classify our field, if our divergence is greater than 0, we call F a source. Because our field is flowing outward at that particular point. If our divergence is less than 0, we call the field a sink. Because the field is tending to flow inward at that point, flowing towards the point. And if our divergence is 0, we call our field incompressible. Because our field, it's not flowing inward or outward. So it's not growing, it's not shrinking, it's not flowing at all. So we call it incompressible. So there's our finally our physical interpretation of the divergence. Flux per unit volume at a point. Tendency of our field to cause an outward flow, and the magnitude of that outward flow at a particular point. And that comes from the divergence. All right, questions on the divergence here? So again, let me re-emphasize. We use the divergence theorem when we're looking for the flux through a closed solid. So our closed solid has to, our closed region, our surface has to enclose a solid region. We can't use the divergence theorem if we're just talking about the flux through a surface, upward flux through a surface. Same with Green's theorem. Green's theorem has to be used on a closed curve. All right.
Oh.